Hey, if you are new here, this is Chandan and you are watching the learning field. So this is the second lecture of our numerical analysis lecture series for especially for GATE, for CSIR NET and for the SET exam. Okay, so in the first lecture we will just start the numerical analysis, the syllabus and the theory of errors. Okay, so we will give a small discussion on the in this session. Okay, so in this session we will start or we will discuss what the numerical solutions of algebraic and transcendental equations. Okay, and in the previous lecture we already discussed the theory of errors, the different types of errors and some examples of that. Okay, so those who are not watching the previous lecture, I'll share the link in the description and also in the I tab. Okay, so my suggestion is that please start attend the lecture series from the first lecture. Okay, because this will be very helpful for you, and I think I also covered the to the point discussion and some important topics for the GATE exam. Okay, and also we will discuss the previous year questions paper of GATE exam. Okay, and recently we finished the LPB section for the GATE LPB playlist, all the theory parts and the previous year questions paper of GATE from 2022 to 2015. Okay, LPB lecture series are also available in the channel on the playlist sections of LPB, so you can watch the lecture series of LPB and PIQs also. Okay, so let's start, and before starting I am requesting that if the content helps you a little bit, then please give a like to this video, share with your friends and subscribe the channel. Okay, so let's start. So we start the numerical solution of algebraic and transcendental equations. Okay, so first consider the problem of numerical computation of the real roots of the given equation. Suppose fx equal to 0 is an equation and we have to find the real roots of this equation. Okay, so and by numerical analysis, using the numerically or numerical analysis. Okay, so which may be algebraic or transcendental. Also assume that the function fx is continuously differentiable and differentiable a sufficient number of times. Okay, so if alpha is the root of the equation fx equal to 0, then we say that f alpha equal to 0 because the root satisfied the given equation. Okay, and say that f dash alpha is not equal to 0 since it is a simple root, that is the root is of order 1, that's why this derivative, first derivative, is not 0. And we also say that the root is a multiple root of order, suppose m, then what, f dash f up to mth order alpha, this is not equal to 0, then we said that the alpha is a multiple root of order m. Okay, so here is a theorem related to these roots. Okay, so the theorem says that if fx is a continuous in closed interval ab and if fb are the opposite signs, are of opposite signs, then there is a real root alpha of the equation fx equal to 0 such that a is less than alpha is less than b. Okay, so if further fx is differentiable in ab, then either f dash x is less than 0 or f dash x is greater than 0 in the open interval ab. Okay, then what, then fx is strictly monotonic in the closed interval ab, then the root alpha is unique. Okay, so this is the theorem related to this result roots. Okay, so now it says that all the methods of the numerical solution of the equations is to be described here, that is in the numerical solution section or in this chapter. Okay, numerical solution of algebraic and transcendental equation, with the exception of one called the Graphis method, will consist of two stages. Okay, so there are two stages mainly. Number one is location of roots and the second stage is the improvement of the rough value of the root. Okay, in the location of roots at which the rough values of the roots are obtained. Okay, suppose you catch one value, rough value, which is you take as a root and then improve the values up to the certain accuracy of desire of accuracy. Okay, that means what, that means suppose you have to correct the roots up to 4 decimal places, here 2 decimal places, here 2 significant digits, significant digits. So we this is the called the desired accuracy rate. Okay, so we have to calculate up to order this, there up to the 4th decimal place or 2 decimal place. Okay, so this is a situation. Okay, so each root to any desired degree of accuracy. Okay, this is the desired degree of accuracy. Suppose we have to calculate the up to 2 decimal places. Okay, so that means after 2 after 2 consecutive iteration, if the 2 decimal places are gives the same value, then we stop the process on that time or on that iteration. Okay, so this is the case of desired degree of accuracy. This is known as degree of accuracy. Okay, so to find the location of roots, we basically apply 2 methods. One is method of tabulation and second one is graphical. So if possible, we draw the graph, but some functions there are no strict graph of the function, so in that case we obviously apply the method of tabulation. And but in some cases it is possible to draw the graph, and if it is possible to draw the graph, then finding or locating the roots is to be very easy in that case. But in all the case, the graph is not so much easy. Okay, that's why in that case also we apply the method of tabulation. Okay, so basic concept of iteration process. What is the basic concept of iteration process? Okay, so let xn be the sequence of iterations of recurrent roots alpha of the equation fx equal to 0. Okay, produced by a given method. The error epsilon n at the nth iteration is defined by epsilon n equal to alpha minus xn. Okay, so this is the error epsilon n at the nth order iteration. Okay, so the iteration converges even only if this epsilon n tends to 0 as n tends to infinity. In case there may be a case in case xn does not converges to alpha, that is, then the method of computation fails and we say that the iteration is divergent. Okay, so when the method is divergent, we say the method is divergent when this epsilon n does not tends to 0 as n tends to infinity. That means the limiting value of this epsilon n, that is the error, the limiting value of error, if it is not goes to 0, then we say that the method is not converges or the method fails to be convergent. Okay, so this is the case. Now given a method of iteration, our primary task is to find the condition under which the iteration convergent. So we have to find the condition in some cases. So this is called the condition of convergence. Okay, this is very easy thing, and these terms are very important for the study of numerical analysis. Okay, so we may try to express epsilon n plus 1 in terms of epsilon n minus 1, which is called the error equation in each case or in each methods, and in each method we calculate the error equations. Okay, now we comes to a very important term, which is order of convergence. Okay, so what is the order of convergence? The iterative method is said to be of order p or has rate of convergence p if p is the largest possible real number for which there exists a finite constant c not equal to 0, such that mod of epsilon n plus 1, which is less equal to c into epsilon n mod epsilon n power p. And if epsilon n plus 1 and epsilon n satisfies this relation for any real number c not equal to 0 or for any finite constant c not equal to 0, then we say that the method has order of convergence p. Okay, where epsilon n equal to xn minus alpha is the error of the nth iteration. Okay, the constant c is called the asymptotic error constant. So this c is also very important and play a very important role here. Okay, now we comes to the first method of our topic, which is bisection method. Okay, you all know the bisection method. I just here go through a simple and a straight cut discussion of bisection method. Okay, and a short discussion on bisection method. So this method is based on the repeated application of intermediate value property or intermediate value theorem. If a root of fx equal to 0 lies on the interval I0, that is, this is the initial interval in which the roots of the equation fx equal to 0 lies, this is equal to a0 b0, we bisect the interval I0 at the point m1. Suppose here if we take, this is suppose the interval a0 and b0, if f of a0 and f of b0 is less than 0, okay, so then we bisect the interval at the point suppose m1, which is equal to a0 plus b0 by 2. Now we calculate the values at this point, at this point, and at this point. Okay, so in each case we check whether this f a0 or f m1 or f m1 f b0 is less than 0. in that case, in which case this relation satisfies, we take this interval further and proceed further. Okay, so this is the main thing of bisection method. Suppose we get f a0 into f of m1, this is less than 0. Okay, so we discard this thing and we proceed further by taking this interval, and the name of the interval, suppose I1 and I2 and I3 and so on. Okay, so this is the funda of bisection method, you all know that. So it is very easy process. Denote by I1 the interval a0 m1. If a0 if m1 is less than 0, then we denote this interval a0 a1 by I1, and if m1 b0, that is if f m1 if f b0 is less than 0, then we take the interval I1 as m1 b0. Okay, so then we bisect the interval I1 and carry on the similar process. I just take a first process and first case and first step, and you carry on. You all know that this process is very easy process. So after nth step, we get this epsilon n is less equal to b0 minus a0 by 2 to the power n. Okay, so that since b0 minus a0 is a fixed constant, and 2 to the power n 1 by 2 to the power n says this is tends to 0, therefore epsilon n tends to 0 as n tends to infinity. That is the iteration converges. So this is the, this says that the bisection method is converges. Okay, and you note one thing, that bisection method is always convergent. Instead of this is a slow method, but bisection method is surely convergent. Okay, and this is a linear convergence method, that is the order of convergence of bisection method is 1. Okay, so we apply this process up to our desired accuracy of the root is arrived. Okay, of the root is arrived. That is the similar funda, we just discuss it. So let us take an example. Let us take this example fx equal to this case. So here we first check, we have to guess first whether the location of roots. Okay, so this is the process of guessing. So suppose we check f0 equal to 0 and f1 is less than 0, therefore the smallest positive root lies in the interval 0 and 1, because f0 and f1 this is less than 0. Okay, that means the root lies in the interval open 0 1. So take a0 equal to 0, b0 equal to 1, and calculate m1 equal to this 0.5. So now we calculate the value of at m1. So this is equal to this minus of this. That means the value of a0, this is greater than 0 and this is less than 0. That means product of this is less than 0. Therefore we take the interval I1 is this one 0 and 0.5. So this is suppose 0 and this is suppose 1. Okay, we find we bisect the interval at 0.5 and we calculate these values at f of 0.5. Since this is greater than 0, this is less than 0, therefore we take this interval as I1 and this is discarded, and we proceed further using this similar process. Okay, so we now calculate m2 and m2 equal to 0.25. Since f m2 equal to 0, therefore we take this and this 0.25 and we proceed further in this similar way. Okay, so the root lies in 0 and 0.25. If we write a table, if we calculate the values, suppose this first 5 iteration of the methods or of the roots, if we find the first 5 iterations, then we calculate this f1 a n minus 1, b n minus 1 and mn, and calculate m in fn and fn minus 1 whether it is greater than 0 or less than 0. If it is less than 0, then we bisect that interval and discard the remaining interval. Okay, so this is the complete process, and if we take this, so the root lies in this interval. Since this 2 is less than 0, this is 0.1875 and 0.21875. Okay, the root lies between in this interval. So the approximate root is taken in the midpoint of this interval. Okay, so this is the root. Suppose if we take, if we stop this process, that is if we stop this iteration at 5th step, okay, you can proceed further to get a higher accuracy rate. Okay, so this is the bisection method. I think you can understand the bisection method. Now we comes to the second method, which is secant method. Okay, so consider the first degree equation fx equal to a0x plus a1. So this is a very equation. You can say that this is very easy to finding the roots, but this is numerical process. Okay, if we need to calculate the roots numerically by or using the numerical analysis, then how can we calculate the roots? This is the method. Okay, this is the different types of methods. How can we calculate the roots numerically? Okay, so suppose you can get an equation which is not easy to find the roots of the equation, which is a first degree equation, but you can't find the root very easily, so that we can use this numerical methods to calculate the roots. Okay, so xn minus 1 and xn are two approximations to the roots. Then we determine a0 and 1 by using the conditions, these conditions. Okay, if n minus 1 equal to this, we just put the values, or we just put the values xn minus 1 instead of x and xn instead of xn instead of x. Okay, now solving these two equations, we find the values of a0 and a1 in terms of fn minus 1, xn and xn minus 1. Okay, so we find the values a0 and a1 by these two values. Okay, now from 1 and 2, that is from the given equation this, and from this equation the next approximation xn plus 1 to the roots is given by xn plus 1 equal to, we just put the values n plus 1 and here, and then put the value change n by n plus 1 and then put the values here. Okay, so if we calculate by this process, then we can write this equation as the form xn plus 1 equal to xn minus xn minus 1 by fn minus 1 into fn. Okay, for n equal to 1 to n. Okay, so this is the process of secant method. You just need to remember this rule, okay, or this computation or this method. Okay, so this is called the secant method. Now geometrically we represent the secant method very clearly. Okay, so suppose this is a graph curve y equal to fx curve. Okay, so geometrically the point where the straight line of the secant joining xn yn, so this is suppose xn yn point, and this is suppose the point xn minus 1 and yn minus 1 cuts at x-axis at the point xn plus 1. This secant cuts the x-axis at xn plus 1. For the secant, the equation, that is the equation of this secant, is very easy. Y minus yn, this yn minus 1 equal to x minus xn by xn minus xn minus 1 intersect y equal to 0 at x equal to this point. Okay, that is intersect this y equal to 0 at which point? At x equal to xn minus yn into xn minus 1 by yn minus 1. This is the geometrical representation of the secant method. Okay, so this is equal to xn plus 1. Okay, so this is the method xn plus 1 equal to xn minus fn or yn minus yn into xn minus 1 by yn minus 1. Okay, so if we take the similar example, x cube minus 5x plus 1 and lies in the interval 0 1 using the secant method. Okay, so x0 equal to what? X0 equal to 0, x1 equal to 1, so this is x0 and this is suppose x1. If x0 equal to this, if x1 equal to this, so x2 equal to, we just put the values in the given iteration. Okay, iteration scheme. Okay, so x1 minus x0 by f1 minus f0 into f1. So this if we just put the values and calculate, we get 0.25. So the value of f2 equal to this. Okay, so our motto is what? Our motto is this value, that is the value of this f tend to 0 for the values of x. Okay, so we now calculate the similar process, then x3, then x4. Now I here take the 2, 3 and 4, these 3 or 4 iterations. Okay, so f3 equal to, we get f4 equal to 0.000. Okay, so see here this 30 already appeared. Okay, so if we write or if we find the root up to 3 order or 3 degrees of accuracy, that is up to 3 decimal places, then you can take this answer as a root. Okay, and if you proceed further, then you can get also the better approximation, the better results. Okay, so this is the case, this is the example of a secant method. Now we calculate the error equation of the secant method. Okay, suppose xi is a simple root of fx equal to 0. So xn equal to this xi plus epsilon n. Okay, since this is root and this is suppose error. Okay, and this is the exact value in the given approximation scheme. So epsilon n plus 1 equal to, we just put the values, and now expanding this xi plus epsilon, and that is this term and this term by Taylor series expansion with respect to this root xi. Okay, and since xi is a root, therefore we put the values if xi equal to 0 whenever this terms of this quantity occurs. So if xi epsilon n plus 1 equal to this epsilon n into this, we just calculate the values, put the values, and if we take common epsilon n minus epsilon n plus 1 from the denominator of the expression, then this term goes to cancel out. Okay, so we just write epsilon n minus, this is the numerator term and this is the denominator term, this power is minus 1. Okay, this is the denominator term. Okay. So this is equal to epsilon n plus 1 equal to what? Now we just multiply this values. So this is equal to half into this one and plus order of these terms. Okay, so we write epsilon n plus 1 equal to c into epsilon n minus epsilon n minus 1, where we write the value of c equal to this. So this is the simple finite value. Okay, because these are the values at the point xi, f double dash I by f dash I, and higher powers of the epsilon n are neglected. Okay, so this is the error equation for the secant method. Okay, now we calculate the order of convergence of secant method, which is very important. Okay, seek the relation of the form, suppose epsilon n and epsilon n plus 1 का जो relation हो, suppose this type of relation, from the error equation we can take this. Okay, since this is the relation between epsilon n plus 1, epsilon n and epsilon n minus 1. Okay, suppose this is the relation. Okay, so now we put we calculate epsilon n equal to this by putting the value of n plus 1 equal to n and n plus n equal to n minus 1, we get these two. Okay, so epsilon n minus 1 equal to, we get this from this equation. Okay, now we put this value to the error equation. So by putting this value in the error equation, we get epsilon n to the power p equal to c into minus a to the power minus 1 plus 1 by p, and epsilon n, this is product. Okay, this is product into epsilon n power 1 plus 1 by p. Okay, now comparing the powers of epsilon n, so we get p equal to 1 plus 1 by p. Therefore we need to find the value of p, which is the order, which gives us the order of convergence. Okay, so p equal to, we get p equal to half into 1 plus minus root 5. So neglecting the negative sign, because the rate of convergence is never negative, so the rate of convergence is 1 plus root 5 by 2. Okay, 1 plus root 5 by 2, which is equal to 1.638. This is very important. This is known as golden ratio. You all know that, I think. Okay, and also the value of a equal to what? C to the power p by 1 plus p. Okay, so this ends the lecture for today. Okay, so in this lecture we just discussed two methods. This is the end of the lectures today. Okay, we discussed the bisection method and the secant method through the examples, and calculate the order of convergence also, and the order of convergence of bisection method is 1, or the bisection method is a linear convergence method. You all know that. Okay. So if the content is helpful, then please give a like to this video, share with your friends and subscribe the channel. मिलते हैं अगला वीडियो में. Thank you.